Let us now consider a slightly complicated circuit and see how one can use the method of generalized steady state analysis. So, the complication is a minor one, it is just adding a resistor on the AC side, but it will result in a complication that means it will result in the presence of one term which was not there in the previous case when there was no resistance on the AC side. So, we will consider this circuit. I have on the AC side a 3-phase balanced voltage source and this is in series with so in each phase there is a series resistance and an inductance. R is the resistance, L is the inductance. So, the only addition now is the resistance. So, the rest of the circuit is same as what we considered earlier. We have 3 legs and 2 thyristor valves in each leg. There is no change in the model of the DC side. So, on the DC side we have a constant current source I D. So, these are valves 1, 3, 5, 4, 6, 2. So, as in the case of the previous circuit where there was no R, here also we can consider 2 modes of operation, 2 and 3 valve conduction mode or 3 and 4 valve conduction mode. Suppose I take 2 and 3 valve conduction mode. So, I can take any cycle and each cycle will have 6 intervals and in each interval of duration 60 degrees I have 2 sub intervals. So, in the first sub interval 3 valves conduct and in the second sub interval 2 valves conduct. So, let me take the first sub interval. So, in the first sub interval 3 valves conduct. So, if I redraw the circuit diagram by showing only the valves or only the elements that conduct. So, among the 6 valves only the valves 1, 2 and 3 conduct and 4, 6 and 5 do not conduct. So, let me just redraw the same circuit by not showing the valves 4, 5 and 6 that do not conduct. So, valve 1 is in series with the voltage source E A, valve 3 is in series with the voltage source E B valve 2 is in series with the voltage source E c. So, this is the circuit which is obtained from the previous one by just removing the valves that do not conduct, that is 4, 5 and 6. So, if I want to solve for this circuit, I can apply mesh analysis or loop analysis. One of the currents is known, ID is known. So, if I consider the other loop, so I have to consider the state variable or the state vector in the first subinterval. So, what is the state vector in the first subinterval? First of all, what is the size of the state vector in the first subinterval and what is the state vector in the second subinterval? So, I mean going by what we studied in the case of the circuit without resistance, we know that in this second subinterval, in fact, valves 2 and 3 conduct and the current is I d which is constant. So, there is no state variable in the second subinterval. So, x 2 is an empty matrix. So, x 2 is an empty matrix, it is 0 cross 1 empty matrix. So, the size of x 1 is 1 cross 1. Okay. So, it has one element more than that in x 2. So, if it has only one element, which is that element? So, going by our assumption, it is the current through the outgoing valve. The outgoing valve is valve 1. So, it is I 1. So, the current I 1 is the element of the state vector x 1. So, how do we get the other quantities? So, let us apply Kirchhoff's voltage law and get the expression for the other quantities. So, if I apply Kirchhoff's voltage law to the loop consisting of E A, E B, the two resistances R, two inductances L and the valves 1 and 3, then what do I get? L d I 1 by dt minus L. So, the current that is flowing here is I d minus I 1 d by dt of I d minus I 1 plus R I 1 minus R I d minus I 1. So, this is equal to E A minus E B. So, this is by applying Kirchhoff's voltage law. So, I want to bring this to the standard form. The standard form is the first order derivative on the left hand side, the first order derivative of the state variables on the left hand side and the remaining quantities on the right hand side. So, I 1 is the state variable. So, on the left hand side I should have d I 1 by dt. So, if I write this in the standard form, d I 1 by dt is equal to, so let me write a few more steps. If I take the first two terms of the previous equation, I get 2 L d I 1 by dt. So, this is equal to, so there is R I 1 appearing twice. So, if I push that to the right hand side, I get minus 2 R I 1, then minus R I d. If I push it that to the right hand side, I get R I d plus E A minus E B. So, in the standard form I get d I 1 by dt is equal to, so divide the entire equation by 2 L, I get minus R by L I 1 plus R I d by 2 L plus E A minus E B by 2 L. So, this is nothing but minus the right hand side is minus R by L I 1 plus R I D by 2 L. E A minus E B is root 2 V sin omega O T with a negative sign. So, this is minus root 2 V sin omega O T divided by 2 L. So, I can finally write this as d I 1 by d t is equal to minus R by L I 1 plus R I D by 2 L minus V by root 2 L sin omega O T. So, this is in the standard form. Now, from this I can say what is A 1 and what is U 1. So, A 1 is nothing but the coefficient of I 1 on the right hand side. So, which is minus R by L, and U 1 is nothing but the remaining terms on the right hand side. So, that is R I D by 2 L minus V by root 2 L sin omega O T. So, we have got x 1, we have got x 2, we have got A 1, we have got U 1. So, since x 2 is an empty matrix, A 2 is also an empty matrix. A 2 is a square matrix. So, the size of A 2 is 0 cross 0. And U 2 is also an empty matrix, the size is same as that of x 2. So, it is 0 cross 1 empty matrix. Now, we have to obtain f and g. So, there is an equation relating f and g. If I take x 1 at alpha by omega o, this is equal to f into x 2 at alpha by omega o plus t 1 plus g. So, I have to use this equation and find f and g. So, if I take x 1 at alpha by omega, it is nothing but x 1 is I 1, x 1 is I 1. So, I 1 at alpha by omega o. So, what is I 1 at alpha by omega o? So, I 1 at alpha by omega o from this circuit or from this circuit. So, valve 3 is turned on at the instant alpha by omega o. So, till then valves 1 and 2 are conducting. So, the current through valve 1 at alpha by omega o is nothing but I d. So, this is I d. And of course, x 2 is empty. So, since x 2 is empty, f is an empty matrix. So, the size of f is 1 cross 0. So, from the size of x 1 and x 2, I can find the size of f. So, since f is an empty matrix, x 2 is also an empty matrix, the product f x 2 is actually a 1 cross 1 matrix which is equal to 0. So, what remains on the right hand side is g, which is nothing but from the equation I 1 at alpha by omega equal to I d, I get g equal to I d. So, this is for 2 and 3 valve conduction mode. Now, if I take this same circuit and try to see what are x 1, x 2, a 1, u 1, a 2, u 2, f and g for 3 and 4 valve conduction mode. Suppose I consider 3 and 4 valve conduction mode. So, if I take the first subinterval, so this is similar to the 3 and 4 valve conduction mode of the circuit without resistance. So, the only change now is the presence of resistance. So, we can see what are the equivalent circuits in the first and second subinterval. So, let us draw the equivalent circuit in the first and second subintervals by just showing those elements which conduct non-zero current. So, in the first subinterval, valves 6, 1, 2 are already conducting. So, 3 is turned on at the beginning of the first subinterval. So, there are 4 valves conducting in the first subinterval, that is 6, 1, 2 and 3. So, the circuit is having all the elements in the original circuit except for the valves 4 and 5. So, valve 1 is in series with EA and valve 2 is in series with EC, and both the valves 3 and 6 are conducting. So, this is the circuit for the first subinterval. The circuit for the second subinterval is same as the circuit which was used for the first subinterval of the 2 and 3 valve conduction mode. So, okay, let me redraw that. So, here the circuit is having all the elements except for the valves 4, 5 and 6. This is valve 1, this is valve 3 and this is valve 2. So, we have the equivalent circuit for both the subintervals. So, can we say what is the state vector x 1, what is the state vector x 2? Now, it is easy to say what is x 2 because we already considered the second subinterval in the case of 2 and 3 valve conduction mode, because the second subinterval equivalent circuit is same as the first subinterval equivalent circuit for 2 and 3 valve conduction mode. So, x 2 here is nothing but what we got as x 1 in the case of 2 and 3 valve conduction mode. So, x 2 is nothing but I 1. Now, if x 2 has an element I 1, now that element should be there even in x 1. So, the elements of x 2 will appear in x 1. So, I 1 is there, but there will be one more element which is the last element which is not an element of x 2, and that element is nothing but the current through the outgoing valve. So, in this case the outgoing valve is valve 6. So, the current through the outgoing valve I 6 is the last element of x 1. So, I have I 6 as an element of x 1 and there is I 1 here. So, here I have I 1 and of course, this is I d minus I 1. So, I got x 1 and x 2. So, the remaining quantities can be easily obtained if I apply Kirchhoff's voltage law. So, if I take the equivalent circuit of the first subinterval and apply Kirchhoff's voltage law, so I have to find the two currents I 1 and I 6. So, there are 3 loops, one loop current is I d which is known. So, the other loop currents are to be determined. So, if I apply Kirchhoff's voltage law, what do I get? So, let me first take the loop consisting of E A, E B, the resistance and inductance R and L in series with E A and R and L in series with E B and the valves 1 and 3. So, if I apply Kirchhoff's voltage law, I get L d by dt of, so I can also show what is this current. Of course, the current through valve 3 is I d minus I 1. So, current through valve 6 is I 6. So, from that I get the current through E B as I d minus I 1 minus I 6. So, L d by dt of I d minus I 1 minus I 6 plus R into I d minus I 1 minus I 6 minus L d I 1 by dt minus R I 1 is equal to E B minus E A. So, there is one more loop consisting of E B E C and the resistance and inductance in series with E B, resistance and inductance in series with E C, the valves 2 and 6, they are in another loop to which we apply Kirchhoff's voltage law. So, I get L d by dt of I d minus I 1 minus I 6 plus R I d minus I 1 minus I 6. So, if I look at the current through valve 2, so this is I d minus I 6. So, minus, okay, I have shown the current as entering the positive terminal of E C. So, this is plus L d by dt of I d minus I 6 plus R into I d minus I 6. So, this is equal to E B minus E C. So, I will write this in the form of vector matrix equation. So, I will take a matrix and multiply this by the column vector whose elements are the derivatives, first order derivatives of the elements of x 1, that is d I 1 by dt and d I 6 by dt. So, my intention is to get the equation in the standard form. So, in the standard form I have only the derivative of the state variables on the left hand side. Okay. So, in both the equations that we have derived, so from these two equations I am getting this. So, I have to see what are the coefficients of d I 1 by dt and d I 6 by dt in the two equations. So, if I take the first equation, the coefficient of d I 1 by dt. So, there is minus L d I 1 by dt, there is one more minus L d I 1 by dt. So, the coefficient of d I 1 by dt in the first equation is minus 2 L. The coefficient of d I 6 by dt is minus L in the first equation. Similarly, in the second equation, the coefficient of d I1 by dt is minus L and the coefficient of d I6 by dt. So, there are two terms minus L d I6 by dt. So, this is minus 2 L. So, I push all the terms all the other terms to the right hand side. So, what do I get? So, the remaining terms I will split it into two categories, one which involve the state variables I1 and I6 and the and those which do not involve I1 and I6. Okay. So, if I first take the terms involving I1 and I6. So, in the first equation what is the coefficient of I1? So, if you look at the first equation, there is a minus R I1 and one more minus R I1. So, if this is pushed to the right hand side, I get 2 R. Similarly, the coefficient of I6 in the first equation, there is a minus R I6. So, since this comes to the right hand side, it is R I6. In the second equation, the coefficient of I1 is minus R. So, when taken to the right hand side, it is R. The coefficient of I6 in the second equation is minus 2 R. So, when taken to the right hand side, it is 2 R. And the remaining terms are, so there is a R I D in the first equation. So, if I push that to the right hand side, it is minus R I D, then E B minus E A. In the second equation also there is a minus R I D. Of course, there are two places where I get R I D. So, it is minus 2 R I D plus E B minus E C. So, I can write this as, so the right hand side is 2 R R R 2 R I1 I6, and if I simplify after substituting for E A and E B, I get minus R I D plus E B minus E A is root 2 V sin omega O T. Of course, I have been using the same expressions for E A, E B and E C, which I have been using even for the simpler case of 0 resistance. So, see what I meant was, if I look at E A, E B, E C, I have not changed the expressions for E A, E B, E C. They are still root 2 by 3 V sin omega O T plus 150 degrees. This is root 2 by 3 V sin omega O T plus 30 degrees, and this is root 2 by 3 V sin omega O T minus 90 degrees. So, with these expressions for E A, E B, E C, E B minus E A is root 2 V sin omega O T, and E B minus E C. So, this is equal to root 2 V. So, E B is root 2 by 3 V sin omega O T plus 30 degrees, and E C is root 2 V root 2 by 3 V sin omega O T minus 90 degrees. So, this is root 2 V sin omega O T plus 60 degrees. So, from this I can get A1 and U1. So, what I need to do is pre-multiply, I am sorry, I made a mistake here, this is plus. I have to pre-multiply both sides of the equation by the inverse of this matrix, square matrix, which is appearing on the left hand side. So, that means pre-multiply by minus 2L minus L minus L minus 2L inverse. So, I get d I1 by dt d I6 by dt on the left hand side. So, that is what we want on the left hand side, which is the standard form. This is equal to minus 2L minus L minus L minus 2L inverse 2R R R 2R into I1 I6, that is the first term. The second term is minus 2L minus L minus L minus 2L inverse minus RID plus root 2 V sin omega OT minus 2 RID plus root 2 V sin omega OT plus 60 degrees. So, this is the equation in the standard form. So, from this we can get the required matrices. So, from this I can say what is A1, what is U1. A1 is nothing but the coefficient of this column vector I1 I6 on the right hand side. So, A1 is minus 2L minus L minus L minus 2L inverse 2R R R 2R, and the second term on the right hand side is U1. So, U1 is minus 2L minus L minus L minus 2L inverse minus RID plus root 2 V sin omega OT minus 2 RID plus root 2 V sin omega OT plus 60 degrees. Now, this is A1 and this is U1. Now, can I say what is A2 U2 by using some previous result? So, A2 and U2 are obtained from the circuit diagram applicable for the second subinterval. Now, this is nothing but the equivalent circuit for the first subinterval of 2 and 3 valve conduction mode. So, what we got as A1 and U1 for the 2 and 3 valve conduction mode are nothing but A2 and U2 for the 3 and 4 valve conduction mode. So, I can straight away write what is A2 and U2 for 3 and 4 valve conduction mode. So, A2 is equal to A1 for 2 and 3 valve conduction mode. So, what was that? And U2 is nothing but U1 for 2 and 3 valve conduction mode. 2 and 3 valve conduction mode. So, if you look at 2 and 3 valve conduction mode, we got U1 as RID by 2L minus V by root 2L sin omega OT. So, the same thing is valid here. RID by 2L minus V by root 2L sin omega OT. So, we have got x1, x2, a1, u1, a2 and u2. So, the only remaining quantities are f and g. So, again we have to find f and g which relates x1 at alpha by omega o and x2 at alpha by omega o plus t1. So, the equation is this. So, in our case x1 is I1 and I6. So, I want to relate the left hand side which is I1 at alpha by omega o, I6 at alpha by omega o. So, this is equal to f into x 2. x 2 is nothing but, so what is x 2? So, just now we saw what is x 2, x 2 is I 1. So, for the second subinterval the only state variable is I 1. So, it is I 1 at alpha by omega O plus T 1 plus G. Now, there are a few things that we know. If I take I 1 at alpha by omega O, what is I 1 at alpha by omega O? Say at alpha by omega O 3 starts conducting. So, at alpha by omega O I 1 is nothing but I d, this is I d. Now, if I take I 6 at alpha by omega O, now I can relate actually I 6 and I 1. Say whatever happens to I 6 happens to I 1 after 60 degrees, which is nothing but the uppercase T with a subscript 1. So, I can say that I 6 at alpha by omega O is nothing but I 1 at alpha by omega O plus T 1. So, from these two equations I can say that I 1 at alpha by omega O, I 6 at alpha by omega O, which is there on the left hand side, is equal to I 1 at alpha by omega O plus T 1. So, one can easily see that the size of F is 2 cross 1. So, there are 2 rows and 1 column. The size of G is also 2 cross 1. So, one can say that the first equation is I 1 at alpha by omega O is nothing but I d. So, I will put that I d in G and 0 as the coefficient of I 1 at alpha by omega O plus T 1. So, in the second equation I 6 at alpha by omega O is nothing but I 1 at alpha by omega O plus T 1. So, I put a 1 in F and 0 in G corresponding to the second equation. So, we get F as 0 1 and G as I d 0. So, if I have a resistance on the AC side, then the equations are slightly complicated. Now, what is the complication? See, if there is no resistance, then you would have noticed that there is no A 1. See, the coefficient of the state variable on the right hand side is 0. So, if you take the 3 and 4 valve conduction mode, we have a non-zero A 1, non-zero A 2. So, if there is no resistance, so you can see that if there is no resistance, this A 1 and A 2 are 0 matrices. So, that is the simplification that you get by neglecting resistance.